Okay. The lecture today is on shape analysis, and so it will sort of finish or continue off the things that we've worked on over the last few weeks. There were some changes made to the slides before because there were some things I added to them to hopefully make it a little clearer and then to have a very quick UNet example. And so this is not a deep learning course. You will not become an expert in deep learning, but this is something that is very, very commonly used today in image analysis competitions for segmentation. And so if you look at places like Kaggle, where they're giving you $1 million if you can come up with the best lung cancer algorithm, or a recent competition where you had to segment outlines of cars, these are the algorithms that are working the best. And so it's not using a Otsu automatic threshold. It's not using histograms. It's using these complicated networks. And so we had sort of the examples before where we would sort of, build these pipelines that you can see here, where you sort of have the different features you add to your image and then maybe a random forest to predict it. And so what we do is then sort of one step beyond that, and you end up getting sort of segmentations like this, which isn't terrible, but it doesn't seem to have really fundamentally grasped the concept of the structure, and it's difficult to improve that model more. So we could get more training data, but it would be very time consuming to put in, and it wouldn't necessarily give us a better result. And so UNet is this sort of, this model in particular, and this entire class of models, where basically you have an image coming in, you have convolutions taking place, downsampling, concatenations, upsampling, and so you handle your image at different resolutions in order to account for the fact that some features are local patterns, and then some features, as you get further down, are more global patterns that need to be learned. This is a simple model you can make for it. This is using a tool called Karis, but most of them look fairly similar. It has TensorFlow in the background, which is what makes all the computation go very, very quickly. And so here what you can see is you have your image coming in. We can specify the size. So if we specify 128 by 128, it'll be a bit more readable what's coming in. And that we have our original image coming in. We perform some filters on it. We downsample so that the image goes from being 128 to 64 by 64. We then do more filters and sort of continue making a model like this. And so you go all the way down to 32 by 32, where you have the deepest sort of feature space. So you've come up with lots of features to classify this image, and then you come back up again. None. So what none means here, this is just more of a tool-specific note, but what none means is that you can put any sized image in. And so if you specify the size, it builds the network for just that size image, but that means you can't put another dimension image in. If you put none in, you can put any kind of image in, which is very helpful for us because it makes it a lot easier to sort of pick the resolution that makes the most sense and create a bunch of tiles and run it that way. But of course, if you have none, then it just shows you none everywhere. And so it's very difficult to see what size components are connected to what. You can also choose another representation to show it. This is sort of the summary representation, where you see all of the layers, and you see the number of parameters each layer has. And so we sort of talked about this idea before of like curve fitting. And with this is the number of free parameters you're trying to fit for in each one of these layers. And you have at the bottom sort of the total number of parameters in your system, and then the total number of trainable parameters. And so for this model, we have 470,000 trainable parameters that we try to fit and optimize to do a better job of segmenting the image. Yeah.
What's a non-trainable parameter?
So non-trainable parameters, you can specifically tell it certain layers aren't being trained. So this is commonly used if you use a model that someone already, so it's something called transfer learning. If you use a model that was trained on a really large data set like ImageNet, you can have that as the beginning and say it's not trainable. And so it would be, if you have 470,000 parameters and you have one piece of training data, it's probably not likely that your model will do a very good job. And so you want to figure out ways to minimize those parameters. Because the more parameters you have, the more sort of things your network is capable of learning, and potentially the less useful your network will be for your problem, because it's very easy to overfit. So we have kind of exactly what we did before. We have this training image and this validation image. So we sort of take the top half to train, the bottom half to validate. This is not good practice. You should actually be using different images. You want to have many examples. Particularly, you don't want to have the exact same measurement in the training and the validation, because you could just be learning noise patterns. So this is just a very simple example for the course that makes it very easy to run interactively. And you could flip it. And so if you have an untrained model, you can put your data in and see what it predicts. And so basically you'll get random noise if we do that. Every time the model's initialized, it has a slightly different set of initial parameters. But basically what we see here is that it did not predict anything. It actually did a pretty terrible job. So it said most values were around the middle. It says the part that was actually part of the cortex was not part of the cortex, and the background was. And so that's kind of what we would expect. It's a random model. It's just randomly multiplying and adding values together. This is not what makes neural nets interesting. What makes neural nets interesting is that we can improve it. We can take each one of these 470,000 parameters and improve it with training data. And so here we have to pick a number of things that we don't really cover in this class. So the first one is this loss function. So this is what we also talked about before with kind of the difference between classification and regression. And so it's how do you penalize bad results for your algorithm? And so here we use mean squared error, but you could also use mean absolute error. You could use pixel accuracy. You could use better metrics like sort of the overlap of what it predicted with the actual output. There's thousands of different metrics that you can use for that. We just use mean squared error because it's the simplest. The optimizer, we use here stochastic gradient descent with a learning rate that's fairly high so that you can see in a notebook actually how it works. And then we have the last part of sort of the metrics. And so what are we measuring each time this runs through? And so here what we want to have is the accuracy. So how many pixels were classified correctly as either being part of the cortex or not. And then the mean absolute error. And so that what we can do here is now run this model where we'll see sort of the training take place. It takes 4 seconds per iteration. You can see the initial accuracy is fairly low, but it jumps up quite quickly. So it goes from 17% to 82%. And because we've split the data, we can see the accuracy here, which is the accuracy for, which is the accuracy for the training data. And here is the accuracy for the validation data. And so that's the data it wasn't explicitly trained on. And so having that gives us some idea what the model's actually able to do on data it hasn't seen before. We can then go here and plot the results. These curves will sort of look different every time based on what your initial parameters were. But what we see is that sort of we had kind of this, these large fluctuations, which are very common, where it sort of took steps that made it better, and it overstepped, and then it got worse, and then it took steps in the other direction with the parameters to try to improve, and then it ends up kind of swinging around. And so this is an example of where the learning rate is too high, and sort of where the algorithm did significantly better on the training task So here's the mean absolute error, here's the mean accuracy. Then the validation tasks are areas that we should be concerned about. This is sort of a sign that maybe we've learned things that are not relevant for the problem and are just relevant for that specific example. And so whenever you're doing tasks like this, with or without neural networks, sort of understanding what's the relationship between this training curve and this validation curve is quite important. And if your model performs really, really well on training data, but really poorly on validation data, it's a terrible model. I mean, this is what k-nearest neighbors does, and it's incredibly simple. And so appreciating what these differences are, how much you should train it, when you should stop, what you should tweak, is of course something for a different course, but at least to have the awareness of how this fits in with what we're doing. So then we can sort of run the model and actually see how it does on the whole image. And we see that it does a fairly good job, depending on how picky you are, at segmenting the cortex out. And so it seems to have understood generally kind of what a cortex is. And what's even more impressive about this is that it doesn't have any position information. So the models we were fitting before, we were basically telling it where each pixel was. With this UNet model, one of the great parts about it is it's just acting on regions of pixels. And so when we look at what comes in, at no point do you have any pixel-specific information. It's only looking at little regions. And so those regions get bigger as you downsample more, but there's fundamentally no, this pixel should do exactly this. But yeah, so that was just so that you've seen UNet. It will come up in some of the exercises, and you'll certainly hear about it a lot when you run into real imaging problems. There's, of course, better versions of this. There's 3D versions of this called VNet, so for volumes. And there's models that claim to do even better. So if you look at those slides, they have changes that they make where they change certain layers or they change how things are configured or how deep the model is. But fundamentally, this approach is what's been very successful in these kind of contests. And it's something you should be kind of generally aware of because it is a very useful tool to have, particularly if you have access to lots of data. So we'll now go to the actual slides. Oop. Not the one. The actual slides for today. So today there's a few more references to look at. This is a topic that is fairly old. Nothing we're covering is brand new or particularly state-of-the-art, but they're still very important techniques. And they're particularly important when we look at the lecture that's coming next week with this high content screening, because these are the kinds of things you actually want to extract when you're doing that analysis. Sorry, not next week, but the next lecture. So I'd recommend looking into these links if you're interested in learning more or having more background on this. So when we sort of look at the previously, we started off with image enhancement. We then did segmentation, and we spent quite a bit of time on these different segmentation methods, how we can process these images, what approaches are available, and covered those in a fair amount of detail so that you should at least feel aware, if not yet comfortable, with how those problems can get solved. And so for today, what our objectives are kind of sort of how do we quantify things about our objects. And so now that we've segmented them, we want to start to do analyses on them so that we can begin to think about doing statistics and comparisons and checks and all of these other important aspects for actually building a paper. How can we say something about the shape? How can we compare different objects of different sizes? Compare two images on the basis of shape calculated from the image. And then what we'll get into in the next lecture is sort of how we go beyond this with tasks like meshing or making pretty renderings or interface analysis and things like that. And so in terms of kind of the outline of what we'll try to cover, sort of object characterization, center extents. We'll talk a bit about anisotropy and how that fits into what we're doing. The shape tensor, principal component analysis. So this will cover it in a bit broader sense because I think it's a very important statistical tool to understand. And then we'll cover specifically what it means for the data that we have. Ellipsoidal representations, scale-free metrics, and then we'll see how far we get with those last few topics. So our motivation kind of goes back to the very first slide in the lecture that we had with, we have these experiments that we've done. We've collected these huge data sets. We have 56 gigabytes per sample. We do the segmentation task, and if it works perfectly, we've now classified our image into sort of 1 bit. So for each pixel, we know if it's part of the bone, for example, or not. And now we have sort of 1.7 gigabytes per sample. And it's still a huge amount of data. And of course, it's interesting to look at. It's massively simplified because we've removed a lot of the noise and artifacts that we're not interested in. But it's still not something we can use. If you're trying to write a paper or compare samples, having 1.75 gigabytes is a lot of data to try to process or do something meaningful with or even visualize. And so when we go back to what we were interested in doing in the first place, it was this idea of sort of a single number. That having a giant image is a good starting point, very good for qualitative analysis. But if we want to do anything quantitative, we need a single number. And so we might be looking at volume fraction, cell count, average cell stretch, cell volume variability, any number of different metrics, but they all fundamentally go back to this single number. And so how can we extract these single numbers from our images? So the first kind of important technique to cover here is this idea of component labeling. So we've mentioned it before. It showed up briefly in a few of the previous exercises. And it's this idea that once you have a segmented image, you want to break it up into separate components. And so, if you have an image like this, you're building a self-driving car. You want to be able to identify other cars on the road. Let's say you build a really fantastic neural network that's able to take this image and segment out just the cars. This is already a very impressive accomplishment. And now you end up with these sort of separate regions in your image. And, if you had a simple task of counting how many cars are near you now, how would you go about doing that? Any ideas? Yeah.
I mean, in this case, you have problems with cars that have instructions, but you could just look for the number of regions that are above the threshold.
Yeah.
Separate regions, as it were.
And how would you find out if they were separate or not?
You'd have to look at the neighborhood of each point.
Yeah.
So, essentially start in the middle at one high point and then go until you reach an edge, and then that's one, and then go to the next one, as it were.
Yeah. So that's exactly what component labeling is. It's really the simplest way to go from some list of objects, pixels where you don't have, for us, you can look at it and you can say, I see 1, 2, 3, 4, 5, 6. That's quite easy for you to do. But if you want to quantify this number, you need to have an algorithm that's capable of doing that as well. And as you mentioned, you do have this problem that if you have a tree or a sign in the middle of a car, then it'll be trickier to identify, is that one car or is that 2 cars? Or particularly here where you have, it looks like 2 cars very close to one another. It's 2 cars very close to one another. And the gap that's sort of covered by the sign is the same almost as the gap between that car. And so it won't be trivial to do this problem, but at least we can sort of see what a strategy there might be. This is actually a much more general problem. If you're looking at Facebook data and you want to figure out, are 2 people connected? You do a similar kind of component labeling algorithm where you go through and you find all of your friends, all of your friends' friends, all of your friends' friends' friends, and determine sort of what the network of this graph is. And you can apply this to roads as well if you're trying to navigate. And so these approaches are very, very general and come up in a lot of different fields. So this is something that's built into most of the tools that we'll use. In MATLAB or scikit-image, it's called label. And you have this idea of sort of a neighborhood inside where you have this, what does it mean to actually be connected with something else? And so just like we talked about in earlier lectures, you have this neighborhood that you need to define where you can look at it as being sort of a distance, so where you give it kind of an array of how far away it can be, or sort of a number of hops that, this is hop 1 and this is hop 2 if you want to get to diagonal elements, and a number of other approaches that you can take. And so if we apply this algorithm to our image, we can then see that it goes through and it's able to color each object in a different color based on if it's separate from the other objects or not. So that's exactly what we're trying to do. Once we've done this, we can also figure out the size of the different objects by sort of making a very simple histogram. And so once you've done the labeling, you can see how big your different components are by just counting the number of pixels that fall into that group. So it gives you a very quick way of seeing what the size distribution is, and for example, identifying that there's these 2 very small components. They're probably not cars, or at least not complete cars, and so you can leave them out. Or if you're building a self-driving car, they're small enough that they're far away, and so you can potentially ignore them if you're not driving too fast. And so we start off basically with the same result we have from segmentation, where we've identified everything as foreground or background. And so, as with the case with the self-driving car, the images aren't only cars or not car, but we have to pick sort of what is our foreground and what is our background. And so for this, we'll say everything that's a car is foreground and everything that's not a car is background. So we'll start with a very simple example here, where we have sort of this X with a gap missing in the middle. And we'll basically go through and label everything 1, that's part of the object, and everything 0, that's not part of the object. We then have this sort of fairly straightforward algorithm where we basically say for each point in the foreground, we want to give it a unique label. And so we want to identify each point uniquely. There are, the approach that you mentioned where you said you find a point in the middle and you sort of grow out to the edges also works. There's a number of different ways to implement this, but this is, at least I found, to be one of the most straightforward ones in terms of what you do. So basically what you do is you give it a unique ID. So we know that there's no 2 points in the image that will have the same index in this sense. And so we can now take this, apply this fairly simple rule where we go through all the points in the image. If it's part of the foreground, then give it this index value. And so what this leaves us with is an image where we have 1, 11, 21, 31, and none of these numbers are the same. And so now we've uniquely identified each point in the image. That wasn't really what we were trying to do, but that's sort of the first step. We can then take this image and iteratively go through it in sort of this brush fire style approach, where we take each point that's in the foreground, or each point now that's non-zero, and then go through each point in the neighborhood. And so we have a neighborhood of X and Y. This is usually the same in the entire image, but you could make it change based on where you were if you were dealing with sort of non-stationary processes. And then you say, if this neighborhood is in the foreground as well, so if it's greater than 0, or if this neighbor point is in the foreground as well, set the label of the point to the minimum label of ixy and ix prime y prime. And then repeat until no more labels have been changed. And so, as you see, this potentially isn't a particularly efficient method because every time you go through every point in the image, you check then every neighbor point and find the minimum, but it gives us a result. And so what we can do, we have the algorithm implemented here in incredibly inefficient ways, but hopefully make it a little bit readable, where we basically go through each point if it's part of the image. Then we look at each sort of prime point, one down, one up, for y and x. And then we check that neighbor point. If the neighbor point is also part of the image, then the new value is equal to the minimum of these two. And if the current value isn't the same as the new value, we print a little message to show us that something has changed. And so here we go through and we print out each time we change a label, and we can look at the resulting images. So the first iteration we go through, we see that this one has become a 1 as well. This one has become 49 as well. This one has become 9. This one has become 51. And so that was sort of the first iteration. The second iteration, this one has now become 1 as well. This one has become 49. This one has become 51. And so these regions are sort of growing. The third iteration, we make a few more changes. And so now all of these are 1, all of these are 49, all of these are 9, all of these are 51. And then the fourth iteration, nothing changes. And so it stays exactly as it was before. And now we've identified that there are sort of 4 independent, distinct components in this image. So we can also show this in sort of a more animated fashion where we have sort of the number of distinct groups in the image over time. And we can sort of see visually how this brush fire spreads. So that you have those sort of 1 values creeping down because they're small and going out to the rest of the image. So we can, of course, apply this to bigger, more complicated images, where we take one of the examples of the car that was split in half, and we end up with sort of, this is our input image, everything's 1 or 0, foreground or background, and we identify sort of each pixel by its unique label. So 57, 58, 59, and we see that none of the pixels have the same label to begin with. We can then run our algorithm. It's exactly the same as it was before. We don't have it print out every change because there's a lot of pixels, and so there'd be lots and lots of changes. But that we see here after 8 iterations, it's sort of done. There are only 1 or 2 changes being made, and we see that it comes down to 2 groups. So it goes from 64 to 2. We can then visualize this as well, where we can sort of see these values propagate out from the upper left and cover the whole range of the image. And so these values don't simply stay the same the whole time. They get affected by the one that's nearer to them. But as this goes on, sort of the image slowly fills up, and you end up with only a few labels at the end. So you can, of course, try different neighborhoods with exactly this problem. So here we use a larger neighborhood. So instead of sort of 1 below and 1 above, we have 2 below and 2 above. And so we make that a larger neighborhood. How do you think that will affect the results? If we go back to our original image. Yep.
Skip over the gap.
Yep. So because that has the -2 in it, or the +2, this will be able to see this point, which means it will very likely skip over that gap. So we can now check to see if that's actually true. We also see that it's done much quicker. And so it's after 6 iterations, it's complete. And there's only 2 components that are found. And so by changing the size of this neighborhood, we can make it sort of skip over gaps like that very well. You can also make the neighborhood larger in one direction than the other. So if you know there's gaps with vertical stripes, you could have it be larger in the vertical direction than the horizontal one. We can also take a smaller kernel. For whatever reason, this showed up very small. But where we take sort of this diamond kernel like we had before, where we don't include sort of these 2 hop elements. Does anyone have any idea what will happen if we do that? Going back to this original image. Yeah.
There's that one disconnected diagonal pixel right there, which will end up being a third group, won't it?
Yeah. So we'll end up getting 3 groups, exactly. So exactly the same code in the background that's running for whatever the video. But we start off with this original configuration. Normally we'd expect this one to become part of this group, but because we've removed that diagonal connectivity, there's no way for this point to sort of be part of that group. We also see that it takes much longer to finish, and so it takes 13 iterations instead of just 6. And so if that's really our concern, if maybe you were looking at sort of flood risk, then it wouldn't necessarily, water can't flow through a diagonal point because if each one of these is a box, then the overlap in the diagonal is very small. They don't share a face. They just share a vertex. And so something like flow wouldn't be relevant. And so then it would be important to have a definition of the neighborhood that corresponded with how your system actually works. But if you were dealing with something like fire, there are very frequent examples of forest fires that are able to jump over very large rivers. And so there it would make sense to have a distance between those that allowed that to take place. And so choosing how you make this neighborhood and select it will affect the kind of results you get with your data, and it should be somehow linked to the physical model of what you're trying to do and what data you're trying to understand. Because these things do have a very large effect, and particularly if you're dealing with really large, complicated samples, it won't always be possible to go through and visualize all the different components. But when you perform something like connected component labeling, the difference between this pixel being here and here would have potentially massive results, effects on your results, particularly if you're looking at things like the average size. And so here, if you were to calculate what's the average area of a car, if you were to choose a neighborhood of 1, 1, that sort of cross, your average area of a car is, potentially like this size, if not smaller. If you chose the neighborhood slightly larger, then the average area is something between this and this. And if you chose the neighborhood being 2 by 2 by 2 by 2, that one in the middle, then your average area is that. And so when you're trying to analyze your samples, something like average area of a component will be incredibly skewed by how you choose, and at least in this case, how you choose the neighborhoods. So sort of beyond it, we can start to perform simple metrics because, with the histogram, we could count the number of voxels or pixels to label the estimated volume. We can then start to look at other things once we have all the individual components, and that's what we'll get into a little bit now. So the first thing we'll cover is sort of the simplest approach, the simplest analysis we can do, which is the center of volume or the center of area, or centroid as it's often called. And so if you're trying to count cells, say something about the cells, compare this to other images, it's useful to have sort of what's the XY coordinate of what you're looking at. And so, of course, the simple approach is you go through, you take your ID that's relevant. So, if you're looking at group 1 or group 2, then you reassign the group that you're looking at as foreground or background, like we did before. So here you have, group 1, group 2. We'll pick one of these groups to analyze, and we can define a center. And so our center is as simple as it sounds, where it's just the mean of all of the x pixels in the image. And so if this is the vector coordinate of a pixel, and this is sort of the I vector, so the vector in the x direction. Sort of you can get the x, the y, and the z by doing this mean. So we can do this. We can go through the group that we're interested in. We can print out all the x, y coordinates, and then we can calculate the x mean and the y mean. So this is very, very simple. You go through, if it's part of the group you're interested in, you add it to your list of coordinates, and then you can just take the mean of both of those. It's very straightforward. Where this starts to get a bit more complicated is where your objects aren't homogeneous. So for cars, this potentially doesn't make as much sense, or it would make sense if you were looking at, X-ray images of cars where, a lot of the car is made out of plastic and some of the car is made out of metal. And so where the center of volume is in the image isn't necessarily where the center of mass would be. And so there you can account for the fact that these are different by using a weighting factor to account for this. This can also be incorporated if you have some sort of probabilistic segmentation where you're not 100% confident about each pixel. You can use your confidence to help influence the center of mass. Because if you have a giant map of your car and you're really confident on the pixels on the left and you're really unconfident about the pixels on the right, you probably want to calculate your center based on the pixels that you're really confident on and not on all of the pixels in the image. And so this idea of center of mass, we won't really use it in strictly the physical sense, much more in how can you use a weighted average to get a more reliable representation of what's inside your image. So if we take an image like this, where we have sort of this gradient inside, and we calculate the center of volume, that's quite straightforward. And if we use that intensity, so in this case we assume it's density, and calculate the center of mass, that's in a different position. So that we see here, these points are much brighter, much closer to sort of being outside of the image, and these ones are much darker. And so this is potentially a better representation of what the center of the object is than just the pure center of all the voxels that get included. Is that sort of clear? There aren't too many use cases for it, but you see it come up periodically, particularly with approaches that involve lots of probabilistic modeling. And I think the idea is quite relevant because when you're looking at different objects, there will be plenty of times where the pixels themselves are not as good of a metric as the intensity or some other value you can include that gives you a better value for what the center might be. So one of the great things about all of the approaches that we've talked so far and shape analysis in general is that these problems have all been solved hundreds, if not thousands of times before. And so in KNIME, in scikit-learn, in Fiji, in ImageJ, in Cell Profiler, in Aviso, kind of any tool, VTK, ITK, all have ways for dealing with this. And they've already been built up and have been tested and work fairly well. And so if we look at scikit-image, we have this function called region props, which takes exactly what we've been doing. And so it takes a labeled image, and it will give us sort of a shape analysis of all the components inside it. So you can read sort of through the documentation. It takes the intensity image, will give us the weighted, the center of mass as well, and kind of all of these other steps. And so you can spend time looking at this more carefully later. But basically what this means is that for our object, we have this segmented image and we have an intensity image. We can run this region props function and we get a huge number of different parameters out about what's inside this segment. And so here we have one region, we have an area, a bounding box, a centroid, convex area, inertial tensor, labels, moments, major axes, orientations. So there is a lot of different terms that different tools will use for exactly the same kind of analysis, but kind of being aware that all of these things can be calculated for you for free is very useful, and kind of appreciating what's already been developed. So I think we'll take a short break here, unless there's any questions on that first part. No? Okay.